Good afternoon, Professor.
Hello, guys. Nice to see you. So I have just sent you message via Moodle on the final exam. We just finished our brief meeting with instructors. So it will be on Monday, and you will get 2 hours plus 10 minutes. Accordingly, will be increased numbers of problems, and other from that will be pretty much the same procedure as all midterms which you experienced previously. I will also send later additional message, maybe via registrar, because somehow people complain if I send only from via Moodle that not everyone gets it, but I actually don't understand why. However, in any way, I believe most of people already know and remember that we will have soon the final exam. Okay, so last time we discussed in details the Carnot cycle, like each steps which are involved in Carnot cycle, and derived equation for the efficiency of Carnot engine, which eventually showed us that Carnot engine efficiency does not depend on the working substance, so, and also on design of the engine. It's just defined by the temperature of the hot and cold bodies or reservoirs, which are indispensable parts of working heat engine. So that is the main conclusion, and also we highlighted that during first two steps of Carnot cycle, the Carnot engine produces work, like some positive work on environment, and because volume increases, and it's like first isotherm and first adiabatic process, and then second isothermal and second adiabatic process. During these processes, volume decreases, and that's why external environment produces some work on the system. That's why we subtract this work from the initially done work during the first steps of Carnot cycle, and effective work done by Carnot heat engine is the area which is defined by 4 steps, 2 isothermal and 2 adiabatic processes on the PV diagram. So today we come to our last topic, however, for sure not least important, and this is entropy. So it has definitely great importance for you guys, because this topic will be included in the final exam. So you need to try to understand the concept, and also know and understand how to do calculations with this new parameter. Also how it relates to the macroscopic parameters and microscopic parameters. So these are topics we are going to discuss today. And so to start, maybe would be good to say that entropy, it was considered quite kind of a useful concept in thermodynamics at the end of 19th century. But over time, with the development of statistical mechanics and with some achievements in this field, it became clear that concept of entropy as additional state parameter of the system, together with temperature, pressure, volume, is really important and plays a major role in understanding of thermodynamic processes. So, as I mentioned before, second law of thermodynamics historically, originally was defined in the scope of research on and like efforts of understanding heat engines. However, more general definition of second law of thermodynamics actually can be formulated by means of the concept of entropy. And in general, it's a measure of disorder of the system. So the larger disorder of the system, the larger entropy, and larger disorder of the system is observed when the system is under steady state ground conditions. So when we have equilibrium, thermodynamic equilibrium, then the number of possible microstates which describe particles which form the gas, for instance, the possible number of these microstates will be maximum for describing current macrostate, which is in thermal equilibrium. And that's why in an isolated system, there are two opportunities. Either we have reversible processes, and then entropy doesn't change, so it's equal to zero change of entropy. Or we have irreversible processes, and entropy increases, because all irreversible processes, so all processes in isolated system, they always go into the direction of the state with higher probability. And the state with higher probability is more disordered state, which corresponds to thermal equilibrium. So that's why this is the definition of a second law of thermodynamics, where entropy, stating that in isolated system, entropy either doesn't change or it increases, assuming that system goes to thermal equilibrium and the number of microstates which can describe the given macrostate increases, like possible microstates. And that is the reason why, for instance, we don't observe such jumping stones as I discussed with you previously, when we can convert potential energy to kinetic and then to internal by throwing stone on the ground, but we cannot convert internal energy to kinetic energy and push it up by itself. So it defines the direction of thermodynamical processes. So this is a general definition and introduction to the concept of entropy and its relationship with thermodynamic, with the direction of thermodynamic processes. And now we will go for more quantitative description, because we definitely need it to solve problems in future on this topic. Okay, I changed the camera, and like if we consider a very small change of state of the gas, for instance, or any system, where some reversible process, then we can write that and write the small change in entropy, which is denoted as capital S, is equal to change in the energy transferred by heat during this reversible process divided by temperature. So since we assume very small change in the system, we consider that temperature remains constant. However, if we want to calculate some change of entropy going from state 1 to state 2, or some initial state to final state, which are quite far from each other, obviously we need to integrate. Then we will get, let's say, initial final state ds. This is equal to integral from initial to final state dqrt. So you see that T, like temperature, is under the integral, because obviously it will also change. Of course, depends on the process which is happening, but if it's not isothermal process, a temperature will also change, and that should be taken into account. So if, for instance, we do a like circular cycle integral over a closed path and calculate change of the entropy for our Carnot cycle, this will be change in the entropy is equal to Qi, like energy transferred from the high temperature body divided by high temperature body minus, we can take this absolute values, Q energy transferred by heat from a cold body divided by temperature of the cold body. And since we have shown previously that the ratio UC over QH is equal to TC divided by TH, we can write that this is equal to 0. So change in entropy for fully reversible, like for a cycle process based on reversible processes, like steps, change in entropy is 0. However, this is true only for reversible processes, and for irreversible processes, of course, we will have some dissipation and some losses between the engine, like working substance, and the environment. That's why we can write that change in entropy for isolated system is either equal when it's a reversible process or always larger than 0. So what I mentioned, that in the isolated system, entropy always increases. And this is actually very short definition of interpretation of the second law of thermodynamics. So that this fact always shows us in which direction thermodynamic processes will follow. So now we need to learn how to calculate change of the entropy for different systems. For different processes. We will consider some ideal gas as a model system, And let us go first for isobaric process. So it's more general process when we have change of both internal energy and system produces some work, dq over dt. So this is the definition of the entropy. And for isobaric process, so we have P equals constant. Then we have also ratio of V divided by T is equal some constant. So this we will need later. And now we take into consideration the first law of thermodynamics. So here we can write that we have change in the internal energy plus some small change in internal energy and some small change in some work done by the system. So this can be written as follows. It's 1 over T dE internal plus P times dV. So this is coming from the fact that we have constant pressure. So if we have a PV diagram, pressure volume, then pressure is constant. So on this PV diagram is an isobaric process will look like this, some horizontal line. And if we pick up some initial volume and some final volume, and in between it will be like change of volume will be dV, then work done by the system will be just area of this rectangle. So that's why we replace this dW with P times dV. And now we need to consider the state equation of state of ideal gas. And we know that it looks like P times V equals to nu number of moles RT. And from here we express our constant pressure P. So we get P equal to nu times R times T divided by V. Okay, now we substitute instead of P here, its expression, and get to the next step. It will be 1 divided by T d E internal plus mu RT dV over V. So we also know that we can express change in the internal energy where specific molecular heat capacitance CV times nu times T. So this change in internal energy will be equal to CV times nu times actually since it's change, so we get dt. And now we can substitute this instead of change in the internal energy. And also, while doing this, we can open parentheses, take into account this 1 over t. So eventually we will get Cv times nu times dt over t plus nu r. So t and t we cancel out. It will be dv over v. Okay, so now we got this differential, and we need to integrate in order to find the change of the entropy delta S. Delta S. This can be kind of separated from our main.
Excuse me, Professor.
Yes.
Can I ask a question?
Sure. Yeah. Of course.
Isn't it instead of CV, CP because we're taking isobaric process?
No, because CP also takes into account the work done by the system. But change in internal energy is defined by CV times nu delta T.
Okay, thank you.
Mm-hmm. Okay, so.
Excuse me, also one question.
Yeah, sure.
Using T, I mean, we use initial what T do we use in initial or in final state?
Oh, okay. Yeah, this is good question. This actually we're coming to this point because we need to integrate now. So we see that we have T like temperature in the first term here, and we will integrate both terms in because both temperature and volume are changing. So we need to integrate both terms in different intervals. First term will be integrated in the interval from T1 to T2, like T initial to T final. And also second term is integrated from volume initial to volume final. And then we will, so we cannot take neither first or second because both of them are changing. And that's why we need to take into account this change. And that is done by integrating. Okay, so let us proceed further. So now we come to this point of integration. So it will be from initial state to final state, ds, and this will be equal to Cv times mu times integral T from T1 to T2. Sorry, let's stick here to initial and final temperature. Then will be dt over T plus mu r times integral of dv over v from v initial to v final. Okay, now we have these integrals. We integrate them. And this will be Cv times nu times natural logarithm. This is integral of dx over x is natural logarithm of x. And since we have defined integral, that will be t final divided by t initial and plus nu r natural logarithm of v final divided by v initial. Okay, so we did the integration. Now we technically have the answer. So we can already calculate this change in entropy, but there is a possibility to do some further manipulations in order to simplify this equation when we consider some specific case. And let us consider monoatomic ideal gas. So we remember from previous discussions, we derived this, that CV for like specific molecular heat capacitance is equal to for monoatomic gas is equal to 3-second R. So let us keep this into account and rewrite final equation, this one, taking into account the value for CV on the next slide. So it will be delta S is equal. So instead of CV, we put 3-second R times nu times natural logarithm of T final divided by T initial, and plus mu R natural logarithm of V final divided by V initial. So now we need to recall that we are dealing with isobaric process, and this is true. Ratio of volume to temperature is constant. So that means that V initial to T initial is equal to V final divided by T final. And from here, we can write that T final over T initial is equal to V final over V initial. If this is true, and we see that here we have this is our arguments in the natural logarithm, means that these natural logarithms are also equal. And that's why we can write natural logarithm of V final over V initial instead of natural logarithm T final over T initial. So let us do this. It will be 3-second R mu times natural logarithm of V final over V initial plus mu R natural logarithm V final over V initial. And now we can factor this out. So it will be mu times R times natural logarithm of V final over V initial times 3-second plus 1. And eventually we will get equation which gives us change in entropy for isobaric process of monoatomic gas, 5-second times nu times R times natural logarithm of V final divided by V initial. So if we have diatomic gas, for instance, we need to come back here and consider that CV is already equal to different numbers like 5-second R. And then it will be the same procedure, but eventually we will get just different coefficient here. But this is how you can simplify this initially obtained two terms which define change in the entropy for isobaric process, assuming the features of the equation of state of ideal gas for isobaric process, particularly these conditions here. So you can get with one term, and this is quite convenient equation to work with. So now we are done with the equation for isobaric process. Let us come back to this original equation which we got. So how does it look? Like this one. CV times nu, C delta S is equal to CV times nu times R, natural logarithm of T final divided by T initial, plus then we got nu R, natural logarithm of no, it doesn't have R. Okay. Where did it go? Interesting. I was writing something here, and now it disappeared. Okay, never mind. Let's go to a new slide and again write this final equation with two terms. So it's CV times nu times natural logarithm T final divided by T initial plus nu times R times natural logarithm of V final divided by V initial. Okay, now, so this is the case for the isobaric process, P equal constant. Now let us go for adiabatic process. It's the easiest case. So in adiabatic process, no energy is transferred by heat. So this is equal. That's why delta S is equal to 0. The delta S is also equal to 0 because ds is defined as dq over temperature. So we don't have any change of entropy in the adiabatic process. So then next it will be isothermal process. So T equals constant. So in this case, the integral, like first term of the integral over temperature will be 0 because there is no change in temperature. So we don't have this component, but we have the second component with the change of volume. So that's why, change in entropy will be equal to nu times R times natural logarithm of V final divided by V initial. And you can write it in a bit different form. Sometimes it could be also convenient. It will be nu times r times natural logarithm unity plus delta V, change in volume, divided by V initial. Depends on what conditions are given for you. So now one more process we need to consider. This is isovolumetric process. Its volume is equal constant. In this case, second term will be neglected because it will be equal to 0. There's no change in volume, only change in temperature. So change in entropy will be equal to CV times nu times natural logarithm T final divided by T initial. And this can be written as also as CV times nu times natural logarithm unity plus delta T divided by T initial. Okay, so we considered all specific processes, possible processes which can happen in ideal gas, and you know how to so we derived initially like this set of equations which help you to calculate change of entropy starting from more general isobaric process when both temperature and volume are changing, and also adiabatic, isothermal, and isovolumetric process. So let us try to also introduce entropy from the point of view of from microscopical point of view. So far we were introducing and describing entropy and like change in entropy. Actually, keep in mind that entropy absolute value doesn't make much sense because it's always determined within some constant, something like potential. But what really matters is change of entropy. That's why usually when we are talking about entropy, what really matters is change of entropy. That's why we calculated change of entropy. However, it's done based on so far on the macroscopic parameters. However, we can also consider this from the macroscopic point of view. And in order to do that, we need to consider such model system, some cylinder with a membrane, some membrane. Here we have ideal gas. Also, we have a piston. And this volume is V initial, and volume up to the piston is V final. We have this cylinder and piston made from thermally like isolated material. So we don't have any transfer of energy via walls of this cylinder and piston. So let us assume initially condition like with V initial when we have membrane and gas cannot spread all over the volume V final. So the probability of occupying some space in this volume V initial by any molecule is equal. So there is no some specific rules which defines where molecules can be or not. So it's just randomly distributed. And if we consider that each molecule possesses some volume Vm, it means that there are quite many positions in this volume V initial where this molecule can be located. And this will be defined by the number Wi initial. And this is the ratio between total volume and volume of the molecule. If we have two molecules, so this is for one molecule. If, for instance, we have two molecules in this volume, then the probability, the possible combination of locations for this molecule will be, in this case, omega I in second power. So that assumes that we neglect with a very low probability that molecules will be in the same position of the space simultaneously, which is really low chance because we know that for ideal gas, the volume which molecules occupy in comparison to the total volume is very low. So if following this concept, if we have n molecules in the system, then the total combination of microstates of different positioning of all these molecules, we will call it capital Wi, and this will be Wi in the power of n will be equal to V initial divided by V molecule in the power of n. So now assume that we take out this membrane and molecules are spread all over the volume V final. So this combination of possible microstates V final will increase in comparison to V initial because total volume is increased. So it will be equal to V final divided by V molecule in the power of n. So number of molecules do not change. They just redistribute from smaller volume in a larger volume. So now let us take a ratio between these two combinations of microstates, which describe the two different macrostates, initial and final. So W final divided by W initial will be equal to V final divided by V molecule power of n, V initial divided by V molecule power of n. And from here we can get that it will be V final divided by V initial in the power of n. So now when what we can do, we can multiply this left and right side by Boltzmann constant, and well, first we take natural logarithm of left and right side and then multiply it by Boltzmann constant. So we will get K times natural logarithm of the ratio W final over W initial equals to K times natural logarithm of V final over V initial in the power of n. So taking into account features of logarithm, we can write that this is equal to k times n times natural logarithm of V final over V initial. So now we can actually rewrite once more this equation, like specifically left side, also taking into account that the logarithm of the ratio is equal to the difference of logarithms. That's why we have k ln wf minus k ln wi. This is equal to kn natural logarithm of V final over V initial. So keep this in mind. We go to another slide, and here we need to consider the process which is going on when we take out this membrane. So we have vacuum here. I didn't mention, but I mean before, when this membrane is fixed, here between the piston and the membrane, we have vacuum. Since we have vacuum, there is no pressure. So work is defined like some elementary work. The omega is defined as P dV. And this is the work done by the system, by the gas. Since we have vacuum and P is equal to 0, there is no work done by expansion because there's no pressure. That's why if we write first the law of thermodynamics, change in internal energy will be equal to Q plus omega, and Q is equal to 0. We mentioned that walls are thermally isolated. There's no energy transfer by heat. Work is also equal to 0. So change in the internal energy is equal to 0, means that temperature is constant. So for this case, we consider the previously derived equation for change in entropy, delta S, which is true for isothermal process. T is constant. And this will be nu times R times natural logarithm of V final divided by V initial. So if we have now write again our previous equation which we derived, here it's written K times natural logarithm WF, the combination of microstates which describe the macrostate, final macrostate, minus K natural logarithm Wi, which is combination of microstates which describe the initial macrostate, equal to nu times R natural logarithm of V final divided by V initial. So we have these two equations, and since the right sides are the same, means that the left sides are also equal to each other. So we can write that delta S, change in entropy, is the difference between these two terms. Since this is the case, means that the entropy can be defined as K times natural logarithm of W, and here this W is not work, it's a combination of microstates which define the given macrostate. So this is definition of our entropy where from the microscopic point of view. And another thing, that the combination of microstates which describe the given macrostate is larger when this system is going to thermodynamic equilibrium. So when system possess the most possibilities of microstate realization of the given macrostate, means that in isolated system, we know already that this disorder always increases, and means disorder increases means that this W also increases because we have more possible microscopical states to describe given macrostate, and that means that the entropy will also increase. So from the point of view of a closed system, we can consider universe also as a closed system. And entropy of universe continuously increases, means it goes via some irreversible processes, approaches thermodynamical equilibrium, and that implies that at some thermodynamical equilibrium with minimum energy of the system, means that system cannot do any work anymore, and that implies that like everything what we observe in universe will kind of decompose. Even black holes will vanish at some point, and eventually even elementary particles will be vanished. So they will be all disappeared, and until some emptiness will remain with some reluctant equilibrium thermodynamic radiation, which will also cool down eventually. So the philosophical point, just enjoy your life today and don't waste time in preparing for the final. So any questions, guys? We are out of time already.
Yes, of course. Professor, I don't quite understand the concept of combination of macrostate, you said. I mean, could you
microstates, yeah, which can define macrostates, macrostate condition. So this is, let's say if we have one molecule, so we have certain volume of our chamber and some volume of the molecule. So how you will define so it's some volume, it's 3-dimensional. How you will define how many microstates can describe this macrostate. And that means we need to consider all possible locations of this single molecule in this volume. So it can be here, 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 and so on. So you can kind of fill with this possible location all volume V. And the number of these possible locations will be the ratio of total volume divided by volume of molecule. You cannot fit more molecules than possible locations in this. Yeah, and then if we have two molecules, we have additional molecule. So then we have all options for the first molecules plus the same options for the second molecule. And the combination of these locations of first and second molecule will be their possible number of these combinations will be V divided by V molecule for the first one, then times V divided by V molecule for the second molecule. And that will be V divided by V molecule in the power of 2.
Yeah,
If we
yeah.
yeah.
I understood.
Sure.
I understood. That is why we used power of n. I mean, n molecules.
Yes. Yeah. When we have
clear.
n molecules, we will get to power of n, assuming that molecules do not occupy the same spots simultaneously. But that will be very unlikely scenario.
All right.
Do you have questions?
Actually, I have so many questions written down.
Oh.
I mean, okay. Two questions. Can I ask?
Mm-hmm.
It is actually related to degree of freedom of the gas, of a gas. I mean, if temperature high, degree of freedom, does it I mean increase? As I remember from textbook, there's likely if temperature high, so the freedom is high.
Well, yeah, I guess you are talking about the atomic molecule, and we have temperature dependence of the degrees of freedom of the atomic molecule. Well, temperature is very low. It's the same as degree of freedom of monoatomic,
Really?
like just one atom. It's 3 seconds. Then if we increase temperature, we activate rotational movement, and then we get to increase degree of freedom by 2, so it will be 5 seconds. If we increase temperature to very high level, like above 1000 degrees, we start to activate vibrational modes, so vibrational motion of this diatomic molecule, and add another 2 degrees of freedom. That will be 7 seconds.
So if we conclude, we can have for diatomic gas 3, 5, and 7 degrees of freedom, right?
For diatomic gas, we can have 3, 5, and 7. Yes, you are right.
Oh, what about monatomic and the polyatomic? Doesn't they relate to this?
So you mean this definition of microstates which can
No. I mean about degree of freedom over temperature.
Yeah, if we have some 3 atomic and higher, then we can get more degrees of freedom. That's true. And vibrate specifically in vibrational mode, when we activate vibrational motion of these more complex molecules, they can provide additional degrees of freedom based on the complexity of their structure.
But so sorry for interrupting you.
Yeah.
But in monatomic gas, degrees of freedom can't exceed 3 degrees of freedom.
That
right?
is for monatomic. There is no option that it will exceed 3 degrees of freedom.
Oh, okay.
That can be exceeded only for molecules with more like 2 and more atoms, because we need rotational. So in order to get this first additional 2 degrees of freedom, so to go from 3 to 5, we need to add some rotational motion. And ideal gas, we assume that molecules, if it's monoatomic, that this monoatomic molecule, like particle, let's call it a different way, it doesn't have any size. So we neglect with its own size and consider it as mathematical point. If it's mathematical point, it can spin by itself, but it will not contribute to any rotational kinetic energy. So in order to gain some rotational kinetic energy, in addition to translational kinetic energy, we need to have diatomic molecule.
Okay. Do we consider this in exam? I mean, if temperature is too high, then degrees of freedom.
I would. It's good question. I would say I kind of a bit mentioned here when we go. So when I derive this equation for the change in entropy of the monoatomic gas, and we got 5 seconds here. So why we got 5 seconds? Because we have 3 seconds here plus 1. And 3 seconds is because we have 3 degrees of freedom for monoatomic gas. If it would be diatomic gas in the temperature range when rotational motion is activated, we would have here 5 seconds because we have 2 additional degrees of freedom. And here we would have 7 seconds instead of 5 seconds. If this is the same diatomic gas is at really high temperature, like about 1000 degrees, and vibrational motion is activated, then instead of 5, we would have already 7 seconds. And of course, here this coefficient would also change.
So we actually consider this in exam.
Yeah, exactly. So I just derived this specifically for monoatomic, but you need to keep in mind when we go from CV, because here we have in this equation CV, specific molecular heat capacitance. Here I wrote it's equal to 3 second R. And this is true for monoatomic. If it's diatomic, then CV with activated rotational motion would be 5 second R. And then accordingly, you proceed further in the derivation. So you put here 5 seconds and eventually get 7 seconds here. So this is definitely taken into account because the response of the system to the transfer of energy in any form, of course, will depend on the degree of freedom of molecules.
Okay, thanks. Thank you very much.
You're welcome.
One more question about long kappa.
Yeah, sure.
How is it assessed actually by counting number of points or just separate points for every weekly assignment? I mean,
you mean what is the weight of each problem?
Yeah,
like
I mean,
points you get for each problem.
I mean, if we have 42% for long kappa.
Okay. You mean for weekly assignments? Mm-hmm.
Right. Will it be separated for every weekly assignment or for?
Yeah, I think that we will start with this consideration that is equally distributed with every assignment. then we will see what we eventually get. And since we still don't have full picture, we really don't know how eventually will be calculated, like final grades will be calculated. We will work on this, but for sure it will be equally applied to every student. So everyone will be in the same conditions.
Oh, okay. Thanks.
Okay, thank you for attention, guys, and I wish you good weekend and good luck with your final exam. It was nice to work with you, and yes, today it's our final lecture. Okay, have a good evening and take care. Bye.
Thank you very much. Bye.